This is joint work with Elisenda Feliu here in the audience. In order to start, let me start by introducing the object of study. These are some polynomial systems that have been showing around in this community. They appeared, or they have been named and studied the main properties into these very nice papers. And fundamentally, there are polynomial systems which are defined by two matrices, right? There's a matrix C that we will assume that's full rank, that has rank S. And there's another matrix M that parametrizes the monomials that show up in our polynomial, right? Then there's different parameters that we label with the letter kappa, and there's the M of them. And as a first example to warm up, allow me to give an example of a 2x2 system with only 4 monomials, depending on these two matrices C and M. Okay, so you multiply C by the diagonal of the parameters, and x to the m corresponds to the different monomials that show up, whose exponents are the columns of the matrix M. Okay, once this is set, why do we care about these systems, about this type of systems? And this is a part that I will go fast over because it's the topic of discussion in this seminar, the mathematics of chemical reaction networks. Very quickly, we are studying the evolution of the concentration of different species that interact with a set of reactions that we model by a graph. And each reaction happens at a certain rate constant that we model by the kappas that appeared before. These kappas will be positive values, and the typical model for the evolution of the concentration of each species is this mass action kinetics, which gives some differential equations whose steady states are precisely zeros over a certain vertically parameterized family, where the case correspond, the parameters are the rate constant. Okay. We also might have some additional extra equations now that come from from conservation laws. These conservation laws are some linear equations that use also some parameters B that also need to be positive, and fundamentally from reaction networks, this L corresponds to the kernel, or kernel, a matrix whose rows correspond to the kernel of the matrix C that we started. It corresponds here to the differences, the part here of the concentrations, and this corresponds to its kernel. Now, the topic of discussion, or the property of these polynomial systems that we want to study, is whether there are values of the parameters K and B such that these systems admit or have two different positive solutions, right? The parameters K, the rate constants, and these B's that corresponds to these equations L that in reaction networks we call stoichiometric compatibility classes, must be positive, and they must give rise to two distinct positive solutions. This has been a question that has been widely studied in this community because it's linked to the multi-stability of the network. We have some biological properties. There's just a tiny bit of the literature in here. But of course, one could directly plug this condition of there being two different positive solutions for some value of the parameters into one software, such as, for instance, cylindrical algebraic decomposition, which would transform it into some other conditions and try to solve a certain polynomial system. Of course, these rely on Grobman bases, which have a high computational cost. So we'd like to rewrite the condition of admitting multiple positive solutions in a different term. And some of these works in reaction networks use a certain parameter that's called deficiency that we will not use here, but the key part of using deficiency, especially coming from the deficiency 1 algorithm, is reducing, in some cases, the system to a certain system of linear equalities and inequalities, which is much more convenient than just directly the cylindrical algebraic decomposition that relies on highly costly computation. So in this line of reducing it to a linear system of equalities and inequalities, there's this theory that showed up especially in the thesis of Hayashi in 2011, but also in other works of some students of Feinberg that they called higher deficiency theory or higher deficiency algorithm, in which this reduction is done in higher generality than in the deficiency 1 case, right? So this is substantially better than cylindrical algebraic decomposition, and we'd like to transform this setting of the higher deficiency algorithm to the notation of vertically parameterized polynomial systems so that it allows us to understand it in a better way and also to give implementations and to further develop algorithms for solving the question of multiple positive solutions. Okay? In this line, there are some characterizations that are useful for the understanding that we have of this theory, and they rely on having some notation, so allowing me to give some of the notation that we will need for these characterizations. Of course, we were saying that there are three matrices, C, M, and L, that label a certain vertically parameterized polynomial system. Now, once we had the matrix C, which has rank S times M, then we label as small l the corank. And as we assume that it has rank S, we can write the matrix C in certain row-reduced echelon form, which is basically having, after some row reductions, a first block that corresponds to the identity and then a certain other matrix P. These row reductions don't change the zero set of the polynomial systems, so we can do them. And this matrix P will have S rows and L columns. S is the rank of C, L the corank. We use this matrix C also to parameterize the kernel of the matrix C, which is an important factor of this part of the system, right? Because the diagonal of K multiplied by the monomials will have to be in the kernel of the matrix C, which is labeled by this part. Also, we consider the matrix L, and in particular, this OL will denote the union of non-zero orthants that intersect this linear space defined by L. So these can be different orthants, for instance, a positive orthant with all positive signs in the entries. This could be some orthants that have some non-zero entry, but not all of them. They are non-zero orthants necessarily. And the first characterization, which is something that some of you might have written in other ways, but for the further developments, we need to write it in this way, is the system admits multiple solutions if and only if there are two equivalent conditions. The first one I wrote it just to remark that here, this intersection of the kernel with the positive orthant that sometimes in reaction networks is called flux cone must be non-empty and must have two different elements. But especially the one that we are interested in, the characterization we are interested in is this characterization 3, which says the following. Now, there is a certain row, which is a vector in R to the M. Remember, M, the number of parameters, so the number of columns of the matrix C, which lies in the image of this union of orthants that we considered before. So the image of the union of orthants is defined by some set of linear equalities and inequalities, right? It may be a very complicated union, but it's some set that is defined by linear equalities and inequalities, such that for this row, this certain parametric linear system that we will call characteristic system has a solution. And what is this? So this first part where P mu is positive, it comes from the same matrix P we were seeing before. And the imposition of being positive corresponds to the fact that the element that we are parameterizing is in the flux cone. And this other matrix, A rho, their entries are precisely differences of exponentials in rho. Note that as rho has M entries, then we label the first S entries in one group, and then the last L entries, remember S plus L equal M, and each of the entries of a row is a difference of two of these exponentials, right? So a difference of exponentials. Some of you may have used these as a trick. You've seen these as using some tricks of linear algebra, but the important part here is the difference of exponentials. What's the good thing of that? Now, If condition 3 were to hold, then this would mean that there is some row here. And if there were some row in this set, then the following set, also defined by linear equalities and inequalities, must be non-empty. That's the key point. Now, this first row belonging to this image of the union of orthants, we already saw it. And what is this other part? The signs of the entries must be given by a certain sign pattern. If we have row, we just have to check which is the sign pattern in that given row. But as each of the entries of this matrix A row is a difference of exponentials, then we can see its sign as something linear in row, right? The good properties of the exponential function allow us to transform this sign of a difference of exponentials into a sign of the difference of some of the components in row. Therefore, this condition, once we have fixed a certain sign matrix, will be defined by some linear equalities and inequalities. All right. So the first characterization actually necessary conditions for having multiple positive solutions can be given in the following terms. We fix all the possible sign matrices such that this makes sense, meaning that there is some matrix Q where the corresponding system has a solution and the sign pattern of Q is given by our sign pattern. And for all of these matrices, if these sets are all of them empty, then the corresponding vertical system cannot admit multiple positive solutions. Why? Because if the condition 3 were to hold, then the corresponding row would lie in some of these sets. Okay? Maybe, perhaps the most interesting part of this work is to give a converse of this statement. Therefore, if some of these, for some sign pattern, some of these sets are a non-empty, then to derive that what we call the characteristic system has some solution. Okay? However, it need not be true that if some of these sets are empty, then we necessarily have a solution of the corresponding characteristic system, right? We need to do some more tricks. And in fact, what we did is to find a certain other set, also defined by linear equalities and inequalities. It might be very complicated and the devil is in the details, but it's also defined by linear equalities and inequalities. There might be unions, intersections, and very complicated things, but it's defined in that way, such that the corresponding characteristic system for a row lying in there does not have any solution. All right. So that set, we can sort of discard it. We can remove it from the set that we started with, and then define this new set CS for which we will try to find solutions of the characteristic system, right? The converse of the previous statement must be coming from the fact that if all of these, if we find some of this CS set that is not empty, we want to find the solution of this thing that we call, that we call the characteristic system, right? Now, of course, things are never nice without hypotheses, so we will have to put some hypotheses in this context for this to be true. What are these hypotheses? Now, these hypotheses also come from the higher deficiency theory, and they rely on a certain graph. Now, this graph comes from the matrix P, and remember here, the matrix P, we chose it because we chose initially a certain row reduction of the matrix C defining the vertical system, so this will rely on this choice that we made. But the assumption is that the graph of this matrix P is a forest. And how do we define the graph? Now we have the rows of the matrix, which are labeled by S nodes, and we have the columns of the matrix, which are labeled by other L nodes, and we form a bipartite graph where there's an edge if and only if the corresponding entry is non-zero, right? So an example, if the matrix P were to be this 3 times 3 matrix, then the corresponding graph would be this bipartite graph, where the blue correspond to the columns of the matrix and the red correspond to the rows of the matrix. And as I was saying before, the assumption that we will make is that P induces a forest, meaning that this graph is a forest. This means that the graph has no loops, all right? Each of the connected components is a tree. Therefore, this imposes high sparsity on the matrix P that we started, right? But from now on, let's just make this assumption. And as I was telling you, perhaps this is a main theorem. If we assume that P induces a forest for some P corresponding to a row reduction, and there exists what we call feasible sign matrix such that the corresponding set CS is non-empty, then for any row that lies in that set, then we are able to find a solution of this characteristic system. And by the first reduction that we did in the talk, the vertical system admits multiple positive solutions, right? Precisely because we found the solution of the characteristic system with rho satisfying that it's in the image of the union of orthons and rho not lying in that other ugly set, all right? Now, very quick proof sketch. Of course, the devil is in the details, but I want to show you how we are using this hypothesis that the corresponding graph induces a forest. Now, we see that if S is what we call feasible, then there exists a certain Q and a solution, an element mu that's positive and lies in R to the L, such that the system, the linear system corresponding to Q, has a positive solution. And what we do is take the solution of this system and try it with this to build a solution of our characteristic system. As we imposed that the sign of Q is precisely S, then if rho belongs to the set CS, then A rho has the same sign pattern of Q. And what we are doing is going equation by equation in this setting and modifying the solution mu in there such that it is still positive and it is now a solution of the corresponding system A mu equals rho. Of course, if you do this in general, then when you go to the following equation of the system, this will not work. The modification will be different and you will never be able to recover a global solution for all the linear equations. However, with this assumption that P induces a forest, which imposes high sparsity on the matrix A rho and on the matrix Q, then we can solve equation by equation, meaning taking one equation, modifying mu for that equation, and then going to the next one and playing with this scalar AI so that this next solution also is a solution of our desired system. Finally, we have to also check that for this newly defined solution, P mu is positive, which is part of the characteristic system, which is where, and here also the devil is in the details, we need to use that rho does not belong to the set DS, right? Rho has to belong to CS, and CS is after subtracting this other set where there are no solutions of the characteristic system. So here, for instance, an example, if Q were to be this one, we would take the first row of this characteristic system, and when we would modify mu in such a way that we have now a solution of this corresponding to this row, and then we would go to the following one, and as the system induces, as P induces a forest, then we can play with this parameter because the mu that we might coincide in the two rows only comes from one possible path in the graph of P. So this was the proof sketch, and let me now go to the last part. So these were already conditions in this theorem which characterize fully when the vertical system admits multiple positive solutions under the assumptions that this P induces a forest, which, as I was saying, imposes high sparsity on the matrix P. And this might not hold, right? However, vertical systems that come from chemical reaction networks and mass action kinetics have many zeros in the corresponding matrix C, right? They might be systems that are actually very sparse. Let me do a quick change of notation. What I was calling before P, now I'll call it P bar. And I want to use it to explain that the hypothesis of inducing a forest might happen for reaction networks or for other systems. But in reaction networks, there's something that usually happens, that there are reversible reactions, which correspond to columns of C that are opposite from each other. So if this happens and these columns have non-zero entries, it might happen that when you do the row reduction and you build C, you again have two columns of P that are proportional to each other, actually opposite in the case of reversible reaction, right? For instance, it might happen that the corresponding matrix P has these two opposite first rows, and therefore we need to do something else, because if as you see here, there are two non-zero entries of the column of these columns of P, then looking at the first 2 by 2 minor of the matrix, we see that this cannot induce a forest. As long as the columns of P have two non-zero entries and are opposite from each other, it cannot induce a forest. However, we may overcome this difficulty by assuming that P has only one representative of each class of proportionality of this P bar. So we take this matrix and we just take one of the representative for each class of proportionality of the columns of P, not only opposite, but also proportional by other scalars. And then for the previous P bar, then we would get this much simpler 3 by 3 matrix, which in this case, it does induce a forest, right? So there's a map that goes from the columns of P bar to the columns of P, sending each column to their representative. And once we have made this simplification of the matrix T, there's another theorem that's similar as before, which would say the following: we define an orientation, which is another sign matrix. If you want to have an intuition of what these orientations are, in the higher deficiency theory, they come from orienting the directed graph that corresponds to the network. But for us, they're just some sign matrices satisfying some conditions. In particular, these conditions that the entries are 1, 1, if and only if the corresponding class of proportionality only has positive elements in their proportional columns. With these orientations, we derive a similar theorem as before for characterizing when the vertical system admits multiple positive solutions. Remember, there exist positive values of the parameters such that there are two distinct positive solutions. And this is if and only if, in this case, there exists an orientation and non-zero row lying in this much more complicated set than before. I will avoid you again the details of that, but first, very important, this set also, as all the sets that we defined so far, can be defined by linear equalities and inequalities. This is important. And such that the corresponding system, which for now we call oriented characteristic system, has a positive solution. So what is the definition of this oriented characteristic system? Very similar as before, but now we add the signs in this part. And if you want to check whether the sign of each of the entries is also a linear function, note that if sigma ij and sigma 2j are different, then the sign of this entry will be determined. For instance, if this is positive and this is negative, then the sign of this will be determined by the sign of P. And if they're the same as before, then the sign is still a linear function that we can define. Once this is given, then very similar theory as before. We define a certain set CS in the same way as before. We define a set for which we can prove that there are no solutions for those row lying in that set. Everything defined by linear equalities and inequalities. And we have the theorem that if P induces a forest, then there exists a sign matrix and an orientation such that the corresponding set is not empty, if and only if the vertical system admits multiple positive solutions. I will start to finish here, just last remarks. Now, everything that I was talking about has to do with this characteristic system. So even if all the hypotheses that we assumed are not true, perhaps one can find other ways to solve this characteristic system. And even if one were to add some nonlinear equations, if these are very few nonlinear equations, this might still simplify the algorithms that we have. So solving this characteristic system is an important step to determining multiple positive solutions. Now, and mu must be positive here. No talk with a typo, without the typo. Some other properties, such as the connectivity of the parameter region of multistationarity or non-degenerate multistationarity, can also, under some hypotheses, be studied using the sets that we define. This is precisely because these parameter sets that we defined, right, these sets CS, from them, using the first theorem, we can reconstruct parameter values and pairs of distinct non-zero solutions of the system. And we can study properties of the corresponding parameter spaces using the corresponding sets. Now, finally, the forest property relies on P. This is a part that we couldn't fully translate yet into vertical systems because we assumed that there exists some P such that the forest hypothesis holds. And this can actually be checked in the higher deficiency theory in any of the row reductions, so in any of the P's that one can build. This doesn't mean that any of the possible P's, if there is one, satisfies this condition, but there's another more complicated condition that can be checked there. And finally, a Julia implementation of checking all of these parameter sets when they're not empty will be available soon. Thanks everyone for your attention.